Assalamu alaikum. Good day everyone. My name is Eman Alshehery. I'm a PhD student at King Abdulaziz University in Saudi Arabia. The title of my work that I will present today is Intelligent Numerical Method for studying MHD Maxwell Williamson Nanofluid flow with biconvection and activation energy. Here, the outlines of this presentation are: number one, the motivation behind this study; number two, the objective of this study; number three, the mathematical formulation of the problem; number four, methodology of solution of the problem; number five, the most important results that I have in this study and its discussion; number six, the conclusion of this study; and number seven, the most important references that used in this work. First, the use of artificial intelligence and its techniques has become most popular in recent times. It's being used to solve problems in various fields, especially in solving stiff nonlinear equations that are considered mathematical models that represent a problem and predict results with high accuracy, efficiency, and speed. Also, the nanofluids play an important role in studying the heat transfer, especially in the field of solar energy and its sources. So, all of this was the reason or the motivation for doing this work. This work aims to study the flow dynamics for two-dimensional magnet hydrodynamic stretched flow of Maxwell-Williamson nanofluid affected by biconvection and activation energy, numerically through intelligent numerical method called Levenberg-Marquardt backpropagation method. For short, we will call it LMPM. Based supervised artificial neural network approach. Here we have the geometrical illustration of flow. The mathematical formulation for the problem was obtained through nonlinear partial differential equations, as shown here. These partial differential equations were transformed into nonlinear ordinary differential equations by similarity transformation variables, as shown here. Here, F denotes the flow, theta denotes the temperature distribution, phi denotes the nanoparticle concentration, and chi denotes the motile density of microorganism, and here we have the boundary conditions of ODE. The solution methodology in this study is implemented in two phases. First, the numerical solutions for the mathematical formulation of a flow model are found by solving ordinary differential equations with boundary conditions for different values of physical parameters, as shown here, through the Lopato method by using this package in MATLAB platform. Here we have the table of the values of different physical parameters. And then second, these solutions were used as reference data or target data through the NFTool package and the MATLAB platform to apply or design the Levenberg-Marquardt backpropagation method or LMPM to study the approximate solution of the flow model through determining the number of neurons, training, testing, and validation data for learning or training the artificial neural networks, which uses, as shown here, 10 neurons, 80% of the data set for training step, 10% for validation step, and 10% for testing step. Here we have the most important of the results that I have in this study and its discussion. First, the accuracy of proposed LMPM is analyzed using the result of error analysis between the target data, which is the solution by Lopato method, and output data, the solution by LMPM, such as number one, the mean square error of the performance for training, testing, and validation process. It's about 10 power minus 9 as shown here at 280 epoch. Number two, the error histogram for different scenarios or values with different cases is about 10 power minus 5 as presented here. Number three, the function fit results show a maximum error for training, validation, and testing data of less than 10 by 10 power minus 5 as illustrated here. The second one, the efficiency of suggested LMPM is studied using the linear correlation or relationship between target data and output data, which given through the regression illustration. We have here the correlation coefficient R equal 1 in training, testing, validation, and all process as displayed here. The third one, the solution of the flow model by LMPM, which analyzes the impact of different physical parameters on the flow velocity, fluid temperature, nanoparticle concentration, and motile density of microorganism, and it can be summarized as flows. Number one, the distribution of the temperature is decreasing for large values of Prandtl number as shown here, and thermal relaxation constant B as shown here. We have here the fluid velocity is decreasing by the magnetic parameter M, but the fluid temperature and concentration of nanoparticle and motile density of microorganism are rising. Here we have the rising value for the activation energy E leads to increase in the concentration of nanoparticle, while the increasing of the biconvection Lewis number LB tends to decrease in the microorganism motile density. Here we have the conclusion of this study. Number one, in this work, the model of the two-dimensional magnet hydrodynamic stretched flow of Maxwell Williamson nanofluid impacted by activation energy and biconvection is studied here by using new numerical intelligent computing approach based on the Levenberg-Marquardt backpropagation method. Number two, the efficiency and accuracy of the designed LMPM for the flow model are represented through error evaluation plots and regression analysis. Number three, the behavior of the fluid velocity and fluid temperature, nanoparticle concentration, and motile density of microorganism functions is shown under the effect of different values of physical factors. The LMPM or the recommended method here in this study has proven accurate and effective in solving nonlinear systems, so we can apply this method for many problems of the nanofluid flow impacted by activation energy, and also for several nonlinear problems in various fields. Here we have the most important references that used in this work. And finally, thank you for your attention.